Okay, now we have our definitions in hand. Let's have a look at our prisoner's dilemma and just have an idea of some of the equilibria that we'll find in the indefinite repetition of this game. So in particular, let's look at a situation where in each period there's a probability p that the game is going to continue to the next period, and a probability 1 minus p that it ends and does not continue. So we will play a period, then after that period's over, we flip a coin, probability p, the game continues, probability 1 minus p, it stops. And then we continue in that manner after each period, deciding whether we continue or not with this random probability. So what kind of equilibria can we find? And in particular here, let's look at subgame perfect equilibria. So let's look for subgame perfect equilibria of this game. One equilibrium, defect in every period regardless of what's happened in the past. So that was a Nash equilibrium of the stage game. It's a Nash equilibrium of the finitely repeated game. So is this a subgame perfect equilibrium of the overall indefinitely repeated game? Yes, indeed it is. Its defect in each period regardless of history is because there's no possible gain if the other player is doing this in any subgame. So start in any period regardless of what's happened in history. If the other player is going to defect regardless in the future, then there's no gain from cooperating in any period. You're strictly better off in any period defecting than cooperating, since you get a strictly higher payoff, and it's not going to affect what the other player does. So this is a subgame perfect equilibrium. It's a very robust one. You perturb what players. One player has no possible advantage to changing their action, given that the other player is doing this. Okay, let's have a look at another equilibrium, which is a little more interesting. And this equilibrium is that we do what's called a grim trigger strategy. So this is known as a grim trigger. So we cooperate until somebody defects, and that's sort of the grim trigger. If somebody defects, then what we're going to do is then we're going to go back to defecting forever. So we'll cooperate as long as the other person's cooperating. Once either of us defects, then we anticipate that that's the end of the game. This triggers an awful outcome. Then we go back to the defect equilibrium forever after, and then regardless of further history. So let's check that this is an equilibrium. So after a history where somebody has defected, so if somebody defected at some point in the future, then we start a sub-game and go forward. Well, we already have checked that always defecting for both players is a subgame perfect equilibrium. So we end up with something which is Nash in every subgame following a defection. So that's fine. So what we need to check in order to make sure that this is a subgame perfect equilibrium is if we start in sub-subgame where the players have cooperated up to this point, is it a best response to cooperate in the next period? So let's check that it's a best response to cooperate if nobody has defected yet. Okay, so what happens? What are my expected payoffs if I cooperate? And I anticipate continuing to cooperate if the other player plays this way. Well, I'm going to get 3 today, 3 tomorrow, 3 the next day, and so forth, as long as these periods continue. So today, I know what's going to happen. Tomorrow, there's a probability p that will continue. Next day, p squared, and so forth. So if I anticipate the other player is cooperating as long as I cooperate, then if I continue to cooperate, I expect this string of payoffs with these probabilities. So let's compare that to what would happen if I defected instead. So suppose I defect instead. Well, what's going to happen? If I defect, then I get the payoff of 5. So remember, our payoffs are if I cooperate, defect, cooperate I get 3, defect I get 5. If the other person's cooperating, if they're defecting, then I get 1 here, 0 here. So I'm going from the 3 to 5. They're still cooperating because we've cooperated in the past, but now I switch to defecting. So at least for one period, I get the 5. But then after that, then we're going to go to the defect forever equilibrium. So then I'm going to get stuck with the 1s. So what we see is I get a 1 period bump up in my payoff, but then I'm going to suffer forever after, because now I've ruined our ability to cooperate in the future, and now we go back to defection. So the question is, when we make the comparison between these two different payoffs, so here's if I keep cooperating, here if I defect, what's the gain? Well, I'm gaining 2 today, right? So I get a gain of 2 today, but then I lose 2 at each point in the future, so my losses are going to be longer. And now whether or not this is a good or bad thing depends on how big P is. So obviously as P gets close to 1, then the loss is going to outweigh the gain, but if P is close to 0, then the gain from defection is going to be higher than the gain from not defecting. So basically at this point it's going to depend on how big P is as to whether or not I want to cooperate or defect. So in order to sustain equilibrium, it's going to have to be that the 2 today that I would gain from defecting has to be less than the loss, the future loss. So if you look at what this sum comes up to be, right? So this is just a sum of a series, a very simple one. So this is just 2 times the sum P plus P squared plus P cubed and so forth, which has value P over 1 minus P if you remember your sum of series. So in this case, what are we comparing? Gain from defection, I gain 2 today. Loss, I'm going to lose 2 in perpetuity forever afterwards. That is has this value, so I'm going to cooperate if 2 is less than or equal to 2P over 1 minus P. And if you work that out and solve that for P, as long as P is greater than or equal to 1/2, then this is satisfied. So cooperate is the best response. So as long as I expect that there to be a higher chance that we're going to continue to tomorrow to then stopping, then I'm willing to cooperate under this strategy. Otherwise, I'm not. So this Grimm trigger equilibrium, how did it work? We sustained cooperation by threatening to resort to permanent defection if cooperation fails. The threat's credible, it's an equilibrium itself, so the whole thing hangs together as a subgame perfect equilibrium, provided that P was greater than or equal to 1/2. So for the particular payoffs we wrote down, as long as there was at least 1/2 a chance of continuing, then we're willing to cooperate, and we got a good outcome. So basically, what do we see from this? If there's a high enough weight on the future, high enough impact on future interactions, then we can sustain behaviors that were not possible in the short run, right? So in the short run, even with finitely repeated games, there was a unique equilibrium to this for the players to defect, and yet when we repeat the game, now we're able to get cooperation out because players can threaten to change their behavior in the future if cooperation is ever broken. So repetition changes the interaction, and it's this ability for players to respond to others' actions that gives the right incentives and allows us to sustain much better outcomes in this game than you can get in finitely repeated or single repetition of the game. Okay, so let's have a look at a slight variation on the same prisoner's dilemma that we just analyzed. And what we're going to do is just change the payoff slightly and see how the analysis changes. So again, there's an indefinite repetition, probability P that the game continues to next period, probability 1 minus P that it ends. And all we've done in this matrix now is change the payoff to defecting when the other person cooperates to 7 instead of 5. So before it was 5, let's up it to 7. So there's an extra 2 gain today versus from defecting versus cooperating. Okay, so what do we end up with in terms of the payoff changes? Well, exactly the same kind of calculation we just did. If I cooperate forever, we're getting 3 in each period. If we defect, the only difference now is I get 7 today, but then we both go to defecting in the future, so 1 thereafter. So the only change in our calculation is now we've got a 4 today. We've still got the 2 indefinitely repeated after that. So the loss is still going to be the 2p over 1 minus p. And so we've got to compare these two and see for what p's we end up with this being a worthwhile defection versus when it's not worthwhile. So again, what we need is the critical point where I'm exactly indifferent between these two things is going to be where 4, the gain from today, is equal to the loss over the future. So 4 is equal to 2p over 1 minus p. You solve that, and you get p is equal to 2/3. And so in order to get cooperation with these payoffs, you need a different threshold. You need p to be greater than or equal to 2/3, whereas before it was a half. So as we increased the gains from defecting in one period, then we need a higher probability of continuing the game in order to sustain cooperation, right? So it's harder to sustain cooperation as the one-time gains from deviation increase. And it's easier to sustain cooperation as the probability that we continue increases. So obviously the future has to matter more, and the gains from the present have to matter less in order to sustain cooperation. Just in order to get some feel for this, there's a paper by Pedro Dalbo in the American Economic Review in 2005. And what he did is he ran some indefinite probability of continuation prisoner's dilemma games where he changed that probability and then saw what happened in terms of people's cooperation in the first period. So just to give you some idea of how that worked, he had one game where it was just a one-shot prisoner's dilemma, and how many people cooperated in the first period. In that case, if there's no chance of continuation, it's actually just a one-shot game. 9% of the subjects cooperated, so 91% of the subjects defected. Then he upped it to 0.5 chance that you continued. It got a higher percentage, so then 31% cooperated in the first period. When he made it up to 3/4, then 46%. So he was getting different reactions in terms of how many people were cooperating in the prisoner's dilemma based on the probability of continuation. Now, of course, there's multiple equilibria here, so it might be that some players were anticipating one thing happening, other players were anticipating something else. So in games with multiple equilibria, it's actually hard to make predictions of exactly what's going to come out, but we nonetheless see that the probability of continuation does affect the behavior in these games, and we know that it allows for different possibilities of continuation as a function of the payoffs.